everyone. Welcome to Asiacrypt 2024 in Kolkata. Kolkata is also known as City of Joy, as you may have heard already. Also, it's called the cultural capital of India. Although we have a very long tradition of academic and scientific activities as well, to name a few, the remarkable discoveries by Shotendranath Bose of Bose Science and Statistics, Acharya Jagadish Chandra Bose's discovery of radio wave communication, and PC Mohalranamish's statistical survey, to name a few. So without further delay, I think we'll just start the program. And Asiacrypt 2024 will be a very remarkable addition to the entire legacy of scientific and academic activities in Kolkata. So I'll just ask Professor Bimal Roy, the General Chair, to come here and say a few words.
Welcome to Asiacrypt 2024 and to the city Kolkata. We are privileged to get this approval from ISCR to host it in this city. And the program co-chairs are there, Sasaki and Kai Ming Chung. They have done a wonderful job setting up an outstanding program. So we are looking for a series of deliberations. And the success of these conferences are in generating mutual collaborations from researchers from various countries, various institutions. And if this platform is used for that, that is going to be the ultimate success. And I hope after this, we'll see many more collaborations which so far didn't really exist. Thank you.
Thank you, Professor Roy. So next, we'll ask Dr. Debashish Roy, the organizing chair, to felicitate Bimal Roy with a token. Thank you, Dr. Roy. So next we have felicitation of the program chairs by the general chair and organizing chairs with flower bouquets. Thank you, Professor Roy and Dr. Debashish Roy. So next, we'll have a short speech by the program chairs, Dr. Yu Sasaki and Professor Kai Min Chung. Please.
Okay, so I'm Yu Sasaki, one of the program co-chairs, and we are very happy to be here and to have a great conference here in Kolkata. And unfortunately, several speakers of the paper will not be able to come due to the visa issues, but they still can present online. So we hope like everyone enjoys the conference. Thank you.
Thanks a lot to the program chairs for the short speech. So next, I'll ask Dr. Debashish Roy for a vote of thanks.
Good morning. Welcome to the City of Joy, as he said, Kolkata. As you know, there has been a lot of works going behind organizing this program. I can't name all of them, but to name a few, first of all, we thank heavily IACR for allowing us to host this conference here in Kolkata after so many years. Professor Bimal Roy, we must thank him because it is all his enthusiasm, guidance, and everything is happening here. The main two hosts are ISI Kolkata and TCG Crest. The papers will be published with the Springer. This iconic venue, Dhanodhanya Auditorium, it has been designed by our Honorable Chief Minister, so Government of West Bengal. DRDO has been working from back end for a long time for getting clearance for all of you to come here. Many other people like Bijoli Grill, Calcutta Rowing Club, Modern Decorators, and Gautam Chatterjee, they have been setting up this venue. We also thank all the distinguished speakers and important personalities who came here from all across the world, the delegates, the students who registered, and many other host of other professors from Pan India will be coming here during this conference. We thank all of them for helping us in organizing this conference. Thank you all.
Okay, thank you, Dr. Roy, for the vote of thanks. So I'll just ask the program chair to take over and start the best paper award session.
Okay, so hello everyone. So let's start the first session of the conference. So in the morning of the first day, we only have the session in this room. And the first session is best paper award sessions. So we have 3 talks and each of them are receiving the best paper award from the conference. Okay, so let's start the first talk that is entitled by revisiting key decomposition techniques for FATE, simpler, faster, and more generic. So the authors are Mariya Georgieva, Sergiu Carpov, Nicolas Gama, Sandra Guasch, and Dimitar Jetchev. And the talk will be given by Nicolas Gama. So please, everyone, join me to welcome the best authors of the first best paper award.
Hello, everyone. So can we have the slides, maybe? Awesome. Thank you. Yeah, so thank you very much. It's really an honor to be able to present at this session. So I'm going to talk about our work with our, so I'm Nicolas Gama from Sandbox AQ. And oh, nice. Can you still hear me? Does it work? Okay. Cool. So, oh.
Yeah.
So yes, I'm Nicolas Gama from Sandbox AQ, and I'm going to talk about our work with Mariya, Sergiu, Sandra, and Dimitar about FHE. Yeah? So it's a very pragmatic question. Fully homomorphic encryption is meant to be the future. It is cited everywhere in Web 0.3, yeah? But it is still a bit slow. Huh? So the big question is, how do we make it faster? Huh? And this goes through efficient multi-precision algebra over the torus. So what is all the fuss about the torus? I'm going to give you a 20-second course about the torus, and then you will know everything about it. So the torus is the set of real numbers modulo 1. So basically, you take a real number, get rid of the integer part, and keep only the decimal part. So you get 0 at the beginning, 0.25, 0.5, 0.75. And when you reach 1, you come back to 0, and then it's periodic. Yeah? So it means that, for example, 0.75 is also equal to minus 0.25. On the torus, you have a distance. You have a notion of when numbers are close or far from each other. So here in this talk, small will mean between minus 0.02 and 0.02. So for example, here 0 is small, 0.1 is small, 0.99 is small, but 0.25 is big. And you can do algebra over the torus. It's going to use a natural vector representation. Just remember one thing, if you do linear combinations, it has to be with integers. And now you know everything about the torus, and I'm going to prove it to you with this quiz. So question 1, can you spot out of these 4 vectors, A, B, C, and D, which one is the smallest? I give you 4 seconds for that. 4, and of course, the answer is 8. Just look at the beginning of the number, 0.0 something, 0.99, we just saw it small. The same question for additions. So I give you 2 vectors, U and V. Which one out of A, B, C, D is closer to U plus V? So here again, it's very simple. Just look at the beginning of the numbers, and you will see 24 plus 33 is close to 57, so the answer is B. So fundamentally, to answer this question, one property that you are using is the prefix property. The fact that it suffices to look at the beginning of the numbers to get immediately the answer. Yeah, same question for 3 times U. So which one is closer to 3 times U? Well, very easy. 3 times 24 is 73. So you get immediately the answer. So you see, that was very easy. Now, let's start with another, do the same exercise with another common representation of numbers for FHE, which is the leveled CRT representation modulo a bunch of primes. So here, it's much harder to try to summarize what is a leveled CRT in only one slide. This is the best I could come up, so it's a summary for engineers. So basically, a number will be a big integer can be represented by either 1, 2, or 3 small integers, modulo respectively Q1, Q2, Q3. If there is only one integer, it means it's a level 1, it's a low precision. And if there are 3, it's a high precision. Then you get a formula to raise the levels. So from level 1 to level 2, level 2 to level 3, it is mostly linear. And you can also decrease the precision. So a magical formula from level 3 to level 2, level 2 to level 1, it's using magical constants. So of course, a researcher will say, why these magical constants? But software engineer will say, great, a constant. That's easier for me. And then you get the notion of if 2 numbers are close to each other or not. So close to each other here means if you decrease the precision to level 1, then the numbers must be, the difference must be up to 20. Then you get multiplication, addition, subtraction. So addition, subtraction, it will work only if the inputs are at the same level. So use this formula to raise or decrease the levels. So let's go for the same quiz. Which vector is closer to 0? Aha, you see that here in 4 seconds, there is no way you can spot the right answer. Not easy. Question 2, which vector is closer to U plus V modulo 1? So here again, if I give you 2 inputs that are not at the same precision, a level 3 and level 2, there is no way you can spot immediately which one is the closer to U plus V. You would have to apply this increase level or decrease level formula for that. And same for 3U, I mean, you get the picture. So it's 3 points for the torus, 0 for CRT. So that's the $1 million question. If working on the torus is simple, why does everyone implement CRT RNS-based FHE mod Q? Is it because CRT FHE mod Q is easier to teach? No, we just saw it's not true. So is it because of security? Is it because of expressiveness? Let's see. So security of ring of LWE. So usually when you think about LWE, you think about the discrete one introduced by Regev in 2005. But if you remember the early course of model Regev, there is something that is striking about LWE. The hardness doesn't come from the algebra. Everything comes from the geometry. And what is this geometry about LWE? Well, you all know this picture. This is linear regression over the real. So you are given a set of points, A and B, the blue points, and you have to fit them over a line, f of A. So if you are in higher dimension, the lines become a plane, so sum of SI, AI. And you all know that over the reals, linreg is easy. Now, let's do an experiment. Take every axis and wrap them around modulo 1, and you will have a problem that transforms into linear regression over the torus, aka TLW, or the ring version TRLW. And once you are over the torus, everything that was easy about linreg becomes hard. There is no more gradient descent, there is no more least mean square, there is no more convexity to exploit. And the problem becomes intractable even for a quantum adversary, and even if the key SI are binary. When the key are binary, you actually get the tightest of all worst case to average case reduction from the binary subset sum. And from this torus description of TLWE, you get an instant reduction. If I give you this as an oracle, you give an instant reduction to every other problem of the LWE family. And the beauty of this problem is that it is completely continuous. The only thing that matters is that the required precision is the noise rate. And when you have a very high noise rate, like bigger than 2 to the minus 40, it is largely easy to represent everything as doubles. So now that you see that picture, should we really scale and round everything mod Q to get the classical LWE? That would not be my first choice. I mean, if Q is too small, the problem becomes insecure because you accidentally can round the noise. If Q is too large, you get something that is inefficient. And even if you choose the perfect Q, just do 1 or 2 operations, Q will not be perfect anymore. So I would discretize it only as a plan B if everything else fails. Now, what can we express about on continuous basis? Well, actually everything in LWE. If you look at the clear text in CKKS, how CKK's bootstrapping used things from Fourier theory and Fourier approximation to approximate the sinus function, how the CKKS Boolean use real-valued polynomial interpolation at the same time as their derivative. So almost everything about the theory of LWE is obtained for continuous spaces and continuous matrix. And the thing is, whenever we take this description and put it in a discrete space modulo Q, all this result gets hindered because suddenly there are artificial scaling and rounding that appears out of nowhere. So let's come back to our questions. Is Q necessary for security? No. TLWE is just enough. Is Q better for the expressiveness? No. So it remains the last possibility. Are implementation more efficient modulo Q? And that's the big point of contention. Up to now, it was true. It used to be, but thanks to this work, not anymore. So let's see why. If we dig into the expression that occur in FHE, basically, the most time-consuming operation is the so-called external product. And inside an external product, you get sums like that, where you have gadget decomposition of something. So that means small integer polynomials times big integer polynomials. You are always modulo something that is like xn plus 1, where n is the power of 2. It can be high precision modulo 1 or big integers modulo Q. And the thing is, the first time we saw this expression, so we we saw that because of that, we had to do some kind of DFT, NTT, or FFT. But since we were over big numbers, the first experiments with GMP or MPFR failed. Whenever we had numbers that are more than 100 bits of precision, basically, if we try to do an FFT or an NTT to that precision, we keep propagating carries, which is not good. So given the carry precision, there was one answer that came out of it. Use full RNS. Basically, if you have a carry precision over polynomials, that will be the answer to life, to universe, etc. And yeah, with this answer, basically, didn't look at the rest of the problem. So what is full RNS? That's a commutative diagram that is used to represent polynomial mod xn plus 1 in large precision. And for that, you combine two mechanisms. One big number mechanism that is using a CRT mechanism, and one DFT mechanism here using entity modulo the same prime. And the two mechanisms are strongly correlated so that all the arithmetic you want to do with polynomial, like addition and multiplication, become element-wise on this space. And that's really efficient because all these elements, mod Q1, QL, are machine world, so everything is supposed to be very fast. And everyone thought that this representation was really the right one at the point that we even started building hardware circuits for FHE using this representation. But suddenly, last year, a paper came out, KLSS 23, so it's Kim, Lee, Seo, and Song. That was proving that full RNS was actually not optimal. It was possible to do asymptotically much better than that. And basically, the reason is if you have an expression like a linear combination of a small thing times a big thing, so the big thing is decomposed modulo all the primes, then you still have to do an entity of the small polynomial modulo each of these primes. So that means L entities. If, however, so you reduce this number so that they are smaller than Q, but then you ignore that you are doing the product modulo Q. You are just doing it over integers. Suddenly, everything becomes much easier because now you will be able to choose one small modulus. So only one entity here will be enough to be able to do the whole product. So L DFT instead of L square. And with that in mind, the biggest term in the complexity vanished. And that's how they made it more efficient. But something that is very striking is how they made it more efficient. They made it more efficient by basically canceling something that was the main strength of full RNS, the strong coupling between the big number mechanism and the entity mechanism. So if that works, that gives some hope that we can do the same actually with decimal representation that is easier to understand. So here is the full question that we should have asked to our oracle. Yes, of course, we have this gadget decomposition, but here we have to take into account that this part, the big part, will be known in advance as soon as the keygen. Only A of X will be known at the last minute. Then indeed, the gadget decomposition is small. It is not big. When we do the sum, we may not do the entire sum. We may cut the sum to a smaller precision. That's the approximate decomposition. And for the result, we may want the result at a lower precision than any of the inputs. And if we take all that in mind, then it's much less clear that full RNS was actually the right answer. And there are two golden rules that come out of it. The first one is that actually we don't need to eliminate carries like we do in full RNS. We just need to delay them and amortize them until they cease to be a problem. That's very different. And the second golden rule is, since we are heavily relying on the gadget decomposition, we should make the output of gadget decomposition our primary representation of numbers. And if we do that, gadget decomposition will become the identity, so that will be very efficient. Of course, the downside is that we may not have a unique representation, but that's something we can work out with normalizations. And the good thing with normalization is that we can run them whenever it is less busy, like after the rush hour. So that's exactly what happens on the torus. So small integer times large precision over the torus. We are going to decompose in base 2 to the k our big number. So this colored thing will be the limbs. They are small. Then we are going to arrange all the limbs into a vector of polynomial that is a small vector. Then, like before, we are going to do this vector, this scalar vector product that are only over small polynomials. So for that, we need only the bounded DFT. And once we get the final result, we are going to remultiply each of the results by the original power. So that's essentially the idea. So in the paper, we make it a little bit more formal. So we are replacing the power by a formal variable y. So we end up with small bivariate integer polynomials over x and y. So why we are doing that? It's because the formalism is better. So when we are a polynomial, if we have a polynomial like that and multiply it by a polynomial in x, by definition, the carry will not move. All the terms in y will remain independent from each other. And when we want to propagate carry, then we consider evaluation using y equal 1 to the 2 to the k. And we are going to proceed as carry propagation using normalization functions. But the other good thing is of working with polynomials is that now we are also able to multiply polynomials in x and y. And these correspond to product over the real lift. And this is exactly the product that occurs in BFV and CKKS. And the nice thing now that we are in polynomial is that there is a fast polynomial multiplication. So these products are quasi-linear in the degree instead of quadratic. So because they are quasi-linear, the product multiplication will remain negligible compared to the external product that remain dominant. So overall, there is no effect on the asymptotic complexity. So thanks to all of that, there are a lot of consequences to this work. At the beginning, we thought that in high multiplicative depth, the only possibility was to combine CRT and entity, that in low depth, it was the opposite. It was to combine base 2K representation with FFT. Now we know that the four are equally valid. They will have the same complexity. And additionally, we can switch from one representation to another. It just costs one external product. So there are other goodies, other results in the paper. I will not have time to describe them in depth. Yes, one reformulation of partial external product combined with the approximate decomposition gives, for example, a 12.5 speedup in the TFHE bootstrapping because it removes this number of FFTs and linear operation. Also, one other side consequence is that now you are able to do parallelizable deterministic FHE evaluations over double floating point FFTs. And if you look at this sentence, it's very rare that you can combine parallelizable deterministic and floating point in the positive sentence. Usually it was believed that once you get two of them, you get automatically the negation of the third. Like parallelizable and deterministic means integers, or floating point and deterministic means not parallelizable. Well, now you get the three, so that's something that is pretty cool. Also, noise level propagation in CKKS can be as smooth as BFV, so that's a benefit of base 2K. We are not constrained by the levels anymore. So is it all theoretic, or is there some practical side of it? Well, there is some practical side of it, and we started the library to prove it. So the library is called the Speculative Arithmetic Library. So it is not an FHE library, but it is an accelerator for FHE. So it is meant to be self-contained arithmetic API, something that is simple to achieve for hardware developer, and at the same time very powerful for FHE. So in the core of the library, the base elements are vector or matrix of small integer polynomials mod xn plus 1. And yes, you are reading correctly, small. They are not mod q, they are really bounded, less than 64 bits, and they do not overflow. Because of that, you get the freedom of the backend choice. Like if you have a backend that likes double floating point FFT, you can. If you have something that prefers fixed point FFT, it's possible. And if you have an entity engine, it is also possible. We are using the versatility of the expression of matrices. So inside of a matrix, we can put either one polynomial or two polynomials or an entire LWE at high precision or a GSW ciphertext. Everything fits in the matrix. You just change the dimensions. And that means that when we do a vector matrix product, it can mean either one polynomial product or one entire external product, or maybe 1,000 external products in parallel, like in PIR. So because of this versatility, it means you will not need anymore to do any cross-operation hardware optimization. Just do the vector matrix product, and you will be able to express everything out of it in one call. So for the front end base 2K versus CRT, we provide normalization functions so that you can use the two worlds for it. So on the product side, we get a lot of possibilities. So scalar vector product over polynomial. So each cell is a polynomial. Matrix vector product. So that's by far the biggest operation. Convolution products or element-wise products. So these are used in different categories of operation over FHE. In case you choose to work with base 2K, the library supports prefixes. So we saw that it was important, the prefix property at the very beginning of the quiz. So yes, whenever you have input a big matrix in memory, at runtime, you can always choose to do a product on a submatrix only, and it will be efficient. And yes, so if we take real life examples, so this circuit is the CGGI bootstrapping. So where you have the gadget decomposition and the product of matrix. So that's the external product. Here you see that we are decomposing A and B, possibly using two different gadgets. So that correspond to one of the optimization of the paper. A and B don't require the same precision, so there is no reason why we would use the same gadgets on the two. And here you see that you are merging the two. So basically that corresponds to a concatenation before the matrix product. So that's the power of matrix products. Below is if you are using the same blind rotate loop for n true. So in n true, basically the B term disappears. So you get something that can be twice as fast. And this is the mapping in code. So that's the actual C code that corresponds to the previous graph. So one box in the graph corresponds to one function call in C. And you see that when you do that, you obtain 5 milliseconds blind rotate loop, so plus 1 millisecond of final key switch, so that's a 6 millisecond bootstrapping for CGGI. And if you do the n through 1, you will get 4 milliseconds. So using the library is very easy. You can do that also in high multiplicative depths. So that would be a CKKS internal product where you get the convolution on the left and the external product on the right to relinearize the results. So that's the same. And now we reach the final conclusion of the talk. So there are lots of takeaways for everyone, for compiler builders, for hardware developers, for everyone. But I think the most important of them is to remember that full RNS is end of life. So due to this work and also previously KLSS 23, circuits that will be based on either of this work will be 1 to 2 order of magnitude faster than circuits based on full RNS. And for the rest of the world, we can finally use base 2K RLWE and live a better life. Thank you for your attention. I hope you enjoyed the talk.
It's working. So again, do you have any question? So can you explain like what kind of services or like products will adapt your method? Do you have any expectation?
Sorry.
What kind of services or like their products will adapt your like?
I did. The,
Can you explain some like applications of the?
oh, application. Yes. So basically everything on FHE. Yeah. So it ranges for TFHE, BFV, CKKS products. Yeah, basically, I think the idea is to start viewing it as an algebra over polynomials of or over small polynomials. So yeah, move away from the hierarchy. There is a GSW, and that is constituted from many LWEs, that is constituted from many polynomials, because this hierarchy is constraining too much the computation on one side. It's actually better if we think of expressing all that into an algebra of polynomials, and that's maybe something that FHE compilers can do.
Thank you. Any other question from the audience? Okay. So we have some like certificate for the best paper award.
Maybe my co-author can join also.
Yeah. He prepared a certificate for all the authors, but currently we only have one. So yeah.
Thank you.
Thank you.
Thank you very much.
Thank you. Nice. Okay. So thank you. Okay, so let's move to the second talk. The second talk of the best paper award session is Unbounded ABE for sockets from LWE Revisited. So the authors are Valerio Cini and Hoeteck. And Valerio Cini is going to give a talk. So please, everyone, welcome the Valerio.
Okay, thanks for the introduction. So I will be presenting this work titled Unbounded AB for Circuits from LWE, and this is a joint work with Hoeteck. So let me start by recalling what AB is. So AB stands for Attribute-Based Encryption, and is a primitive introduced in 2005 by Tsai and Waters. This primitive generalized the concept of public key encryption, in that it allows for a finer grain access control to the plain text encrypted in the ciphertext. And it has the following interface. So there is a setup algorithm, takes as input some security parameter and a class of function capital F. And it generates a public key, a master public key and a master secret key. With the master public key, one can encrypt a message mu together with some attribute X to generate a ciphertext. And then with the master secret key, one can generate some function key for some function F in the class capital F. Then with the ciphertext and the function key, one can run the decryption algorithm. And this is supposed to output the plain text that was encrypted in the ciphertext whenever the function evaluates to true on input the attribute. And by this, we mean that F evaluates to 0 on input X. Okay, so what do we know about AB construction? Okay, and so if the function class, it only contains function with a fixed input length, we say that the AB is bounded. Whereas if the function class can support functions with arbitrary input, we say that the AB is unbounded. So unbounded refers to the input length of the attribute. So what do we know about AB construction? So if we focus on lattice-based construction that are the only one that are able to support general circuits, and we classify the construction based on the following two metrics. So whether or not the construction is unbounded, and whether or not it only uses other cryptographic primitives in a black box way, then we have the following. So the seminal work of Bonnet et al., which I'm going to refer to as the BGG plus construction, constructed bounded AB, but only using other cryptographic primitives in a black box way. 2 years later, the works of Berkhaysky, Lakontanatan, and Goyal, Koppel, and Waters showed how to construct unbounded ABE, but at the cost of relying on other cryptographic primitives in a non-black box way. More specifically, the BV construction used the code of a PRF to homomorphic evaluate it, and the GKW construction used some Gabrielin circuits of an underlying ABE scheme. So in this work, we show how you can obtain basically both properties the same way. So why would that be important? So first of all, if you want to have an implementation of any such scheme, that having a scheme where you don't use other cryptographic primitives in a non-black box way allows you for a more efficient construction and avoiding a lot of implementation hurdles. But more importantly is that if you only restrict yourself to use other cryptographic primitives in a black box way, then this means you have to develop new techniques to handle such things. And the techniques may be independently useful in other contexts. So for example, the techniques used in the BGG plus construction have seen a wide range of applications. And we believe that the techniques that we have developed here could find also the similar applications. So let me start by also describing what the other acronym in the title means. So LWE stands for Learning with Error, and it's a computational assumption introduced in 2005 by Regev, which states the following. So suppose you're given a wide matrix B, where orange means that it's uniform random, and you're also given some random linear combination of the rows of B, to which you add some small error, where green stands for small. Then the assumption says that basically this looks random to the eye of a computationally bounded adversary. And this is the only assumption we are going to use in the work. Before diving into the main technical part of our work, let me recall the BGG plus construction and why it does not achieve bounded attribute length. So in the BGG plus construction, you have a very wide matrix A in the public parameters. And in this work, they showed how you can deterministically compute a matrix A sub F, given this matrix A and a function F. So in their work, they have a ciphertext component of the following form, which I'm going to denote as the BGG encoding of the attribute X. And then they show how you can compute some matrix, some short matrix H, such that the following equality holds. Now, given this equality, you can I can describe basically the construction more in detail. So in the public parameters, you will have a short matrix A0 and a very wide one A, as long as the length of the attribute that you want to support, and a vector B. The master secret key is going to be a trapdoor for the matrix A0. Then in the ciphertext, which from now on I will be denoting without the error terms for compactness, you will have the following three components: SA0, the BGG encoding, and an encoding of the message mu. The secret key for a function f will be a vector k sub f, where the following notation means that the vector k sub f is short or low norm, and it satisfies the following equation. So k sub f is a preimage of B under the matrix A0 with AF concatenated. And now correctness is quite direct. So using the equation below, you can compute you can compute on the second ciphertext component to obtain S times A sub f minus f of xg. And then whenever f of x is equal to 0, this component here vanishes, and you can concatenate SA0 and A sub f multiplied by the key to obtain S times B and cancel out this term and recover the plain text. So what's the problem with the construction? So the problem is that the master public key must contain this very long matrix A, which must be as long as the length of the attribute that you want to compute on. So the idea in our work is to find a way to somehow compress this very wide matrix A, so that the length of the master public key would be independent of the length of the attribute that you want to support. So how do we compress the master public key? So the idea is that you want to delay the sampling of these matrices A sub I, which compose the matrix A, from the setup to the key generation. So if you're able to do that, then the setup will be independent of the length of the attribute. And but how do we are able then to support homomorphic computation on this attribute? So the idea is to add some other extra stuff to the secret key and to the ciphertext, so that during decryption, you can recompute the BGG encoding using these two extra components. Okay. So let me describe a short, a very toy example of how to achieve this, and then I'll discuss why this simple construction is insecure and how we can fix it. So the master public key will be as in the BGG plus construction, except for this very wide matrix A. And in place of this matrix A, we will have three different matrices, B0, W, and B. Then in the ciphertext, we will replace the BGG encoding of the different input of the different bits of the attribute with the following expression. We will have three ciphertext components, where the secret SI are independently random, whereas the secret S is common to all these encodings. And then so this is for the ciphertext part. For the secret key, we will add preimages of B under this matrix B concatenated with W. And we will implicitly define the matrices AI of the BGG plus construction as this G, which can be publicly computed, times Ri, where Ri is the second component of the secret key. Okay, so let me briefly see why this achieves correctness. So suppose you're given this ciphertext component and this secret key, then one can concatenate the first two, multiply by the secret key, and subtract the third one. Then by expressing out what this secret key is, you see that you can obtain Si times B plus Sg times the second part R. But by definition, G times R is this AI. So by expressing everything out, we see that we can obtain the I encoding of the BGG plus construction. And then once you have all this such encoding, you can recollect all of them and run the BGG plus decryption algorithm. Okay, so why such a simple construction is insecure? So first of all, as I presented it, the different key Zi, Ri are not actually bounded to the index I. So a malicious adversary could take the ith component, the jth component of the ciphertext, multiply with the ith component of the key to obtain expression of the form SAI minus XJ times G, for I different from J. And then this leads to some attacks. So a way to fix it is to try to modify these two components to link them to the index that they're supposed to represent. And the way we do this is by replacing W in both of them by W plus IG. So the ciphertext component will look like this now. And similarly for the preimage, we need to get a preimage of the W plus IG part. Okay. Another technicality is that actually the AI that you define with each secret key is different if the RI are different for different functions. So the way we handle this is by adding a PRF key to the master secret key, so that during the the key generation, you can use the randomness generated by the PRF to compute these matrices, so that across different queries, you get the same AI. So this basically concludes the construction. So let me summarize the construction. So in the master public key, we have these four matrices, A0, B0, WB, and this vector B. And in the master secret key, we have a trapdoor for A0, trapdoor for B0, and the PRF key K. Then the ciphertext is given by these two components of the BGG plus ciphertext, and this component for each bit of the attribute I. And in the key, we will have this extra component of the key to basically obtain the BGG plus encoding and the BGG plus key. Okay. Before concluding, let me briefly go through the security proof of the scheme. So in the correctness basically follows as before. So you use these key components to obtain a BGG plus encoding of XI from this ciphertext component here. And once you have all of them, you can run the BGG plus decryption algorithm using this BGG key for the function M. Okay. So let me briefly sketch the security proof. So in the security, you want to show that the ciphertext hides the message that was encrypted computationally, while allowing the adversary to query for functions that do not allow him to decrypt the ciphertext. Okay. And the way we are going to do it is by running a hybrid game for each I in L, where L is the length of the challenge attribute. And in each of them, we are going to replace the ith quantity here with something that can be computed given the ith bit of the ith encoding of the BGG plus scheme and something random. Okay, so we basically only need to focus on the ith component of this ciphertext in hybrid I. So the first thing we are going to do is to replace the matrix W in the master public key that was supposed to be uniform random with a matrix of this form. Now this WI tilde is hidden to the adversary, and by the leftover hash lemma, this looks random to the adversary. Okay. Once we do this, we can replace, we can rewrite this component here as follows. And now we basically we would like to rely on LW with respect to the matrix B0 and secret SI, replace this quantity with random. Okay, so we cannot do this immediately because we are using the trapdoor for B0 to compute the secret key. So we need to show that we are able to simulate the secret key without having the trapdoor for B0. Okay, so how are we gonna do it? So we have L secret key components. So in hybrid I, we are going to sample the ith one, the random Gaussian. And then we are going to use it to define what the matrix B in the public parameter is supposed to be. And then once we do this, we see that we can rewrite the matrix that is supposed to be defining the Gaussian preimage for the other matrices in the following way. And since J must be different from I in the other cases, we see that this matrix WI tilde can be used as a trapdoor for this whole matrix. So you can use the matrix WI tilde to sample the preimages for J different from I. So once you do that, you can replace B0 with a uniform random matrix. Now we can rewrite the ciphertext by denoting this as C1I and this as C2I. Using the decryption equation, you can write the third component as a function of C1I, C2I, and the BGG encoding of the ith bit of the attribute. And then similarly, the C2I component in terms of the C1I component. And then once you do this, you can rely on LWE to replace C1I with random, and similarly C2I with random after C1I is random. Okay, so once you do this for each I in L, you replace everything with random, and now you're left with something that we computed, given some random ciphertext C1I, C2I, and then the BGG plus ciphertext. So then you can simply run the BGG plus security. Okay, so let me conclude by summarizing what we did basically. So we showed that you can construct an unbounded AB scheme from LWE only using a PRF in a black box way. And we show in the paper that the same techniques can be used to obtain unbounded inner product predicate encryption from LWE. And so as an open question, like maybe other application of these techniques in other contexts, this would be nice to explore somehow. Yeah, there was a thank you at the end, but
Okay. Thank you. Thank you for the presentation. So do you have any question?
First of all, nice presentation. So do you have the proof that you showed? Does it like achieve semi-adaptive security? I think like.
yeah, yes, I didn't mention it. Yes, but yeah, so like the BGG plus construction achieve only selective security. So the adversary has to declare the attribute at the beginning of the game before even seeing the public parameters. But all the other construction that achieve unbounded attribute length, they also achieve semi-adaptive security. So the adversary only declares it after.
Because you can still delay the stuff generating. Yeah. And the second question that I had was like does your technique also work with these new techniques for evaluating unbounded depth circuits? So this should be still a leveled circuit evaluation, right?
Yeah. So there is still this dependency on the depth. So you still have as in the other unbounded DB works, you still have this depth dependency in the BGG plus construction. So that
right. So the question was like does this technique like work with that kind of like can you evaluate unbounded depth circuits with this technique as well?
Yes, I think it should work similarly. Yes, but then you would have to rely on these stronger assumptions.
Yeah, of course. Yes. Okay, thanks.
Do you have a question? Yes, please.
Thanks. First of all, very nice paper. Thank you. Second, did you look at applying this technique to broadcast encryption? Is there any potential for improvement of the state of the art there?
有一个不好的地方就是我设的话，我必须要就是我设的这个 A 键，我必须要按 A 过后，然后鼠标是对那个地方，就是跟我玩 AT 感觉不一样。玩 AT 的话，你 AT 版就可以，你这没法 AT 版。我可以 AT 版。
To inner product, inner product functional encryption, but not to broadcast encryption.
Sorry, sorry for some confusion or like some noise from the background. I think we have time for one more question. Okay, so if you have more questions, then please discuss offline. Then we have also have a certificate for you.
这个职业是目前他们说玩的最爽的题目，可以。但是我怎么发现感觉前期有点坐牢，我操，
确实有点累，感觉这个打起来。
是的，感觉他妈战士一直砍就完了。
对，战士走进人群里，你都不用动鼠标。
而且这个它可以
Let's thank the speaker.
WASD 来移动。
Okay, so next talk will be presented online.
我操，我刚才装备了2个东西，感觉不一样。
Yes, can you hear me? 这中国人吧，确实。
Okay, so I will introduce the presentation. So the third best paper award from Asiacrypt 2024 is entitled with the first practical collision for 31-step SHA-256. The authors are Yingxin Li, Fukang Liu, Gaoli Wang, Xiaoyang, and Siwei. And Yingxin Lin will give a talk. So please welcome the speaker.
Yes, can you hear me?
Yes.
Okay. Yeah, thanks for introduction. Yeah, I'm going to present our work, the first practical client for 31 steps SHA-256. The authors are Yingxin Li, Fukang Liu, Gaoli Wang, Xiaoyang, Siwei. And I will this talk will be divided in three parts. In the first part, I will briefly review the SHA-2. The SHA-2 family is a series of hash functions standardized by NIST. The SHA-2 hash function is to strengthen security of SHA-1. SHA-2 has have a more complex compression function, which mainly consists of two versions, SHA-256 and SHA-512. And NIST defines many different truncated versions based on the SHA-256 and SHA-512. And the SHA-2 has been used worldwide, especially SHA-256 is used in Bitcoin. The SHA-256 and the SHA-512 share almost the same message expansion and state update function, only with different state size and different rotation number in sigma. So I take the SHA-256 as an example to explain the compression function. The compression function of SHA-256 has an internal state of 256 bit divided into 8 state words. A state as state is represented as AI, A-1, A-2, A-3, and EI, and E-1, E-2, E-3. The compression consists of 16 steps and at each step, I expanded message word WI is used to update two state words AI and EI. So in the step function, the EI is updated by EMS4, EMS4, and the EMS1, EMS2, EMS3, KI, and WI. The KI is constant and the WI is the expanded message word. And the AI is updated by EI, AMS4, AMS1, AMS2, AMS3. And the sigma 0, sigma 1, F1, IMG are Boolean function. And these four Boolean functions as shown in these four equations. And this is the message expansion of SHA-256, the compression of SHA-256. The message expansion of SHA-256 splits the 512-bit message block MG into 16 words MI is 0, 1, 2, and up to 15, and expand them into 64 expanded message word WI. When I is 0 to 15, the WI is updated by MI. When I is 16 and 64, the WI is updated by WI -2, WI -7, WI -15, and WI -16. This sigma 0 and sigma 1 are two Boolean function, and these two Boolean functions showing these two equations. And this part I will introduce our new clean attacks on SHA-2. Finding a valid attack requires a text to finish the following three tasks. Task 1, select the message difference to construct a local gleason. And task 2, search for corresponding differential trail in WI, AI, and EI. And the task 3, found a gleaning message pair based on the differential trail. Our contribution is task 3 in our work. Found our gleaning message pair based on the 31 steps differential trail. Since our work based on the two block clean attacks, so I will first introduce the two block attack overview. The two block clean attack against the SHA-2 was first proposed by Man at Asiacrypt 20 and 13. In the two block method, the difference appears in the second block. The output value of the first block is used as the input for the second block, and the difference in the second block cancel out, and that's leading to a cleaner. And this I will introduce our new cleaner attacks framework for 31 steps SHA-2. In 2013, Mendel first obtained our 31 steps theoretical clean attacks on SHA-256 use the meet in the middle technique. However, this method requires discretely handling A-1, A-2, A-3, as shown in this figure, the left. This method requires direct handling A-1, A-2, A-3 during both pre-computation and the matching phases, which result a significant memory cost. In contrast, we propose a new clean attack framework called the two-stage memory efficient clean attack framework. In our method, we validated the A-1, A-2, A-3 values that need to be matched step by step. Our new method also consists of the pre-processing phases and the matching phases. The mainly purpose of the processing phase is to find a number of the valid A-1 values and store them in a table, while the matching phases focus on the checking the validity of A-1, A-2, A-3. And next, we will provide a detailed explanation of these processes. And in the pre-processing phases, is to find a valid solution of A-1, A-2 up to A12, the E5, E6, E7, E12, W9, W10, W11, and W12. By only considering EI update function, the I is 9, 10, 11, 12. The and the AI update function is 5, 6 up to 12. Among them, the distinct A1, A2, A3, A4, E5, E6, E7, E8 can be treated as a starting point. In other words, A1, A2, A3, A4, E5, E6, E7, E8 are distinct in those starting points. And the next, when we found the standpoint, we need to find invalid a minus 1 from each starting point. For each obtained starting point, all possible W8, W8 E4 are executed to satisfy the E8 update function. And for the each valid W8 E4 satisfying above equation. Satisfying the E8 update function. Then the corresponding A0 can be computed according to the following relation. That is the A4 update function. For each valid tampons W8, E4, A0, or possible E3, W7 are similar executed to satisfy the E7 update function, and the corresponding A-1 can be computed according to the following relation: A3 update function. This is a matching physics. The matching physics consists of 2 steps, and in the step 1, we can try arbitrary M0 and get the corresponding changing input IV1 for the second block, and thus IV1 is equal to the A minus 4, A minus 3, A minus 2, A minus 1, E minus 4, E minus 3, E minus 2, E minus 1. And step 2, we can check the validity of A minus 1, A minus 2, A minus 3 step by step. And the first we can check the A minus 1. The A minus 1 obtained from IV1 is matched with the pro-computed physics A minus 1. And then we can check the validity of A minus 2 and A minus 3. And we can how to check the validity of the A minus 3 and A minus 2. And the first we can compute the E0, E1, E2 to make the associated E0, E1, E2 consistent with those computed from this V1 according to the following 3 equations: A0, A1, A2. Then, and we can compute the W4, W5, and W6 to make associated E4, E5, and E6 also consistent with those computed from this IV1, and E5 is E4, E5, 6 update function. And the last step, we can check the weather or the condition on E1, E0, E1, E2, W4, 5, 6 hold. And this step we mainly check if A minus 2, A minus 3 can be validly converted into the conditions on W5 and W6. And with the 31 steps differential trial and above under the new memory efficient clean attacks framework, or we can find the first practical cleansing for 31 steps chart 5, 6. And this procedure consists of 3 steps. In the step 1, we can pre-compute the to the power of 19.8 valid solution of A minus 1, A0, A1, A2, A3, A4, E5, E6, E7, E8, and store those tampons in a table. And then the step 2, we can try arbitrary M0 and get a corresponding values of the IV1 to match A minus 3. from A minus 1 from this table, and then we can check the validity of the A minus 3, A minus 2. And this, and here, the everyone is equal to the A minus 4 minus 3 minus 2, E minus 1, and the E minus 4, E minus 2, E minus 3, E minus 2, E minus 1. And the last steps, we can use the freedom in the W15 and 14 to fulfill the remaining conditions. And we can use 1.2 hours with 64 threads to find the first practical cleaning message pair. And the time complex is 2 to the power of 15.5, and the memory of the 2 to the power of 19.8. And this table showing our cleaning message pair for 31 steps SHA-256. This is M0 and M1. Based on the new method, we can improve the cleaning. We can improve the cleaner task on 31 steps SHA-512. So we first use a new method to search a new differential trail sparse in the probability checking part, and use this new method. We can reduce the time complex and the memory complex on 31 steps SHA-512. And this is the summary of symmetry stacking attacks on SHA-2. And in the first result, we can find the first first practical cleaning message pair on 31 steps SHA-256, and we can reduce the time complex and the memory complex on SHA-512. That's all. Thank you.
Okay, thank you for the presentation. So do you have any questions? Do you have any question from the room? So I have one question. So did you actually change the differential trail?
No, I use the previous differential trail. I'm only changes the matching phases.
Okay, so can you show page 16?
Yeah.
So yeah, I'm a little bit confused about the statement, use a new differential trail. So what is about it?
Yeah. This differential, we can reduce the condition in the E3 for the conditions. Yeah.
So you changed. So you changed the trail.
Yeah, we changed the SHA-512 trails.
Okay. Okay. So you changed the trail for SHA-512. I see.
Yeah.
Okay. Thank you. Any other question? So can you give some? Can you highlight the difficulty of attacking 32 steps?
Because for the long steps, we can't find the we can't find the message word. We can't find the message word to inject the difference to find the differential triangle.
Okay, thank you. Any other question? Okay, so the chairs will send you the best paper award certificate by mail. And please, everyone, thank you again for the authors and all the authors in the session.
Yes, thank you.
So that's the end of the session.